Let's now take a look at an example. Let's determine the magnetic moment of the circuit shown below, or rather of our current carrying loop. And so we see we have this triangular path which is carrying 5 amps in a counterclockwise direction. And so if we want to find our magnetic moment or our magnetic dipole moment M, we know that's just equal to IS times our unit normal vector U sub M. And so of course in this case we know our current is 5 amps, so that leaves two things that we need to figure out. We need to figure out our S, which is our loop area, and we need to figure out this unit normal vector U sub M. So this problem is going to focus a little bit more on the geometry and a couple key things there, but I do think it is important for you guys to know how to use a couple of these tricks I'm going to show you. That's why we're going to focus on that, but of course we could relate this back to our torque, which if this was in the presence of a uniform magnetic field, ultimately we could use this magnetic moment that we're going to find and just cross product that with our magnetic field B to get our torque on this current carrying loop. Okay, so let's start by looking at our surface area of the loop S. So in order to do that, let's figure out the length of each of these sides. So let's say each of these sort of straight blue lines has some length which is going to be L. And so to do that, we could look at one of any of three triangles. So for instance, if we look on just our z-axis, just our y-axis, and then just this path here, we know that the length of two of those sides is 2. So let's come down here and so I'm not sure, there, I lost our L there. So let's come down here and sort of just redraw that triangle really briefly. So we have our right triangle here, and this is 2, 2L. And so of course we can say that that's going to be the square root of 2 squared plus 2 squared, or the square root of 8. So now we know the length of each of those sides, and now we want the overall area here. So let's draw this triangle, which has length L on each of the three sides. And so we get something that looks like this, and so this is length L, this is length L, and what I'm actually going to do is let's drop this, and so I didn't draw that very well, but that should be bisecting that triangle such that we have length over 2 on each side there, and let's call this our height. And so now what we can say is that our area is going to be equal to 1/2 the base, where our base is L over 2, times the height, which is just h, and we'll solve for that in a little bit, but we have two of those triangles, right? So that's the area for one of these two triangles, but of course we have two of them, so let's multiply that by 2. And of course what we see is that's going to cancel out with this 1/2 factor out front. So we know that our L is equal to the square root of 8, and so of course this is just going to be square root of 8 over 2 for our L over 2. And so using that, we can determine our h is equal to square root of L squared minus the quantity L over 2 squared, and if we plug in those values, that comes out to be square root of 6. So coming back to our area equation then, we can see that this is going to be square root of 8 divided by 2 for that L over 2 times our square root of 6, which ends up being square root of 12. And so remember, in our equation above, we called that S. Okay, so now the only thing we need to do is to find our U of N. So let's find our unit normal vector, U sub N. So let's talk about a couple general equations. And so this is where it's sort of just handy to know this type of stuff. So in general, if we have a plane intercepting our coordinate axis at certain points, so in general, a plane intercepting our coordinate axes at points, and so let's say on our x-axis it intersects at A, on our y-axis it intersects at B, and on our z-axis it intersects at C. So we have 0, 0C, 0B 0, and A 0, 0 as shown there. And so if that's the case, then we can describe that plane with an equation that is x over A plus y over B plus z over C equal to 1. And so we can modify that a little bit by multiplying through, finding a common denominator, and what we can see is that we have b times c multiplied by x plus c times a multiplied by y plus a times b multiplied by z, which is equal to ABC. So in this particular case, we notice that our a is equal to 2, our b is equal to 2, and our c is equal to 2. And so that's just coming back up here to this initial diagram. We see we're intersecting the z at 2, y at 2, and our x-axis at 2. So all of those ABC terms are just 2 in this case. So we see our answer is going to be kind of trivial, but this is a useful thing to know for sort of more complicated configurations. So what we could do then is, let's say for our case we have a equals b equals c, which is equal to 2. So we can adjust this a little bit because we're going to have, of course, 2 times 2 times 2 over here, so 8. Let's go ahead and each of these terms is just going to be 2 times 2, which is 4. So let's divide through by 4. Again, this is sort of a special case, but we can divide through by 4. So that's going to get rid of all of those terms on the left. So we're just going to have x plus y plus z. And then we would have had 8 over here, but dividing by 4 gives us 2. So again, we've just divided through by 4. So what we can say then is, if we're interested in some point x, y, z, we just move the 2 to the other side. So we have x plus y plus z minus 2 is equal to 0. So we can define some point like that. Now, if we're interested in a perpendicular vector, so we can take the gradient. So a perpendicular vector to our plane f is in general given by plus or minus gradient of f. And so then if we want a unit normal, we can say, of course, our unit normal vector is just going to be plus or minus gradient of f divided by the magnitude of the gradient of f. And so in this particular case, in Cartesian coordinates, we're taking our gradient is just going to be the derivative, we're just taking the derivative of each of those components. And so because we just have x, y, and z, we're just going to end up with 1 in our x direction. So this is going to be plus or minus 1 in our x direction plus 1 in our y direction plus 1 in our z direction. And then that 2 is going to go away, so we're just left with those 3 items there. And so what we do is, if we plug in down here, we can see that the magnitude of this is going to be 3. So we're going to have that same plus or minus u of x plus u of y plus u of z, which is our plus or minus del f, and then the magnitude is just going to be the square root of 1 squared plus 1 squared plus 1 squared, or the square root of 3. Okay, so we've narrowed it down to 2 options because we still have that plus or minus. So remember, now we need to use our right hand rule. So we're going to put our fingers in the direction of our current, which is counterclockwise or anti-clockwise, and we see our thumb is pointing out, or sort of in the positive x, y, z direction. So that means we're going to use our positive sign. So we're going to use the positive, or the plus, from our right hand rule. Okay, so now all we have to do is plug in those 2 results for our s and our unit normal vector. So we know our m is equal to is times our unit normal vector. So our current was given as 5 amps. Our s we found to be square root of 12. We have this 1 over root 3 factor from our unit normal vector, and that's in a direction of 1, 1, 1, which of course we kind of could have expected based on having those axes intercepts at the same distance from the origin. So if we go ahead and sort of reduce that term out front, we end up getting that is 10 times 1, 1, 1, and again the units of this are amps meter squared. And so again, if we then had a uniform B that this current carrying loop was in, we could easily find the torque just by taking that magnetic moment equation and doing the cross product of M with B. And so again, just to sort of get an idea of our unit normal vector, so I'm going to draw this kind of poorly, but it's kind of coming out, so it's in the direction of our origin, coming out in the 1, 1, 1 direction. So it's kind of poor, but it's coming in 1 in x, 1 in y, 1 in z, and so that's kind of what we would expect even before we did any math to determine that.